This is exercise 1.3 from the C programming language by Kernighan and Ritchie. In this section of the book, the authors present a temperature conversion program, Fahrenheit to Celsius. One of the things the authors talk about are the basic data types, the char, the short, the long, and the double. The sizes are machine dependent. We can find out what the size of the basic data types are for our machine. If I look in this directory, I've written a little program here called sizeof.c. Let's take a look at it. Here you notice I've included the header file, limits.h. In limits.h is defined the symbols char max, char min, short max, short min, here written as SHRT, int max, int min, and long max and long min. The size of these data types we can find out by using the size of operator, size of char, size of short, and so on. Let's run this program. And here it tells us the size of the char. It says 1. What that means is 1 byte, so 8 bits. The size of the short is 2 bytes, or 16 bits. The size of the int is 4 bytes, 32 bits. And the size of the long is 8 bytes, or 64 bits. There is, for each, a minimum and maximum value. For the char, 127 is the maximum and negative 128 the minimum. The rest are given here, as you can see. If we wanted, we could look at the file, limits.h. And if we search for the types, we can see here char min, char max, short min, short max, int min, int max, and so on. Let's go ahead then and look at this temperature conversion program. We see here that this program begins with a comment. Comments start with /*. Comments end with //. It is to be noted that comments can run for many lines. So additional comments can be added. And the comment block ends with //. Comments are removed by the compiler. Here's our familiar include stdio.h and our familiar declaration of main. Now we have two variables that are declared as integers. That is, they do not have a fractional portion. Fahrenheit and Celsius. 3 more variables are declared as integers as well, lower, upper, and step. These variables are then initialized. That is, lower gets the value of 0, upper gets the value of 300, and step the value of 20. It is important in C to initialize your variables. If you don't initialize them, then there's no telling what value you will get. Now we begin by initializing the variable Fahrenheit to the value of lower. We know what's in lower, it's 0. So Fahrenheit now has the value of lower. We now come to the beginning of a loop construct. This construction is very typical and is very common. In a looping construct, we will repeat over and over the body of the loop. Here, the body of the loop is defined between these 2 brackets. And we have 3 statements within the body of the loop. We will execute the body of the loop over and over as long as this expression is true, as long as Fahrenheit is less than or equal than to upper. We know that Fahrenheit, upon first coming to the loop, has a value of 0. We know the value of upper is 300. Is 0 less than or equal to 300? The answer is true. Therefore, we will execute the body of the loop. Here is the conversion formula. Celsius equals 5 times the quantity Fahrenheit minus 32, and then divided by 9. Your authors point out that this perhaps looks a bit unnatural. We might have expected 5 divided by 9 times Fahrenheit minus 32. But we note that 5 and 9 are integers. This will be integer division. As a result, the fractional portion gets truncated. Well, 5 divided by 9 is less than 1, and so that fractional portion gets truncated, and we will end up with 0. In fact, why don't we go ahead and test this? And we'll go GCC here. And we see that our conversion has resulted in 0 in all cases. Clearly, that's not what we want. In order to get around this problem, we're going to multiply Fahrenheit minus 32, the quantity, by 5. This will result in a number that is larger than 9. We're then going to divide by 9. This, of course, is an approximation. Let's go ahead now and run this program. Well, that's better, isn't it? Your authors do note that it's not exactly very accurate. They also note that the output is really not very attractive. Here we have, with our printf statement, we have %d. And what that means is that we are expecting an integer. We might think of this as decimal, and that would be fine as long as we don't assume that the decimal has a fractional value. D is used for numbers in base 10, integers in base 10. We can also use I here. Let's go ahead and compile and run, and yes, indeed, we can use I. What if we did specify F? F is used for floating point numbers, or numbers with decimals, that is to say, fractional portions. No, I meant to compile. And the compiler gives us a warning and says, you are trying to use integers with floats. And that's not a good thing. We can, of course, go ahead and run our program, but we're not getting the results that we expected. It's also possible to use the specifier B if we wanted to see binary. Let's take a look at that. Well, that's quite interesting. This is the binary representation of the values. Not what we want in this case. So we can go back to decimal. Decimal, in this case, is meaning base 10. Let's specify a width to try to make this output look a little bit better. I believe your authors recommend a width of 3 and a width of 6. Seems to compile all right. Yes, I think that does look just a bit better. The numbers are aligned. However, the real problem is the accuracy. In order to fix that problem, we should really use floats. And if we're going to use floating point numbers, let's make our expression a little bit more natural. I'll put a space in here to make this more readable. Here we cannot use the D. Let's go ahead and try it anyway. And it tells us that the expected argument of int is not there. Let's see what we get anyway. Well, not exactly what we expect. So now the Fahrenheit variable here, which is a float, will be substituted in for this %3f. The 3 is a width. And Celsius will be substituted in for this 6f. 6, again, is a width. We also want to have some precision. How much or how many decimal places should we see? For the Fahrenheit variable, those values will not have a decimal place. For Celsius, well, your authors give 1. We could make it any number that we wanted. If we wanted to see 2 decimal places, or 3, or 4. And that is more accurate than our integer version of the program. So we begin the program with Fahrenheit less than or equal to upper. Fahrenheit was initialized to lower, which is 0, and upper is 300. So we execute these 2 lines, and then we come down here to the final statement in the loop, which is Fahrenheit equals Fahrenheit plus step. Well, Fahrenheit equals 0. And now we're going to add step, which is 20, and then we're going to assign that to Fahrenheit. So Fahrenheit becomes 20. We come up to the top of the loop. Is 20 less than or equal to 300? And the answer is yes. So we will continue in our loop and increment Fahrenheit again by 20. We will do this over and over until this expression, Fahrenheit less than or equal to upper, becomes false. In exercise 1.3 now, they tell us, modify the temperature conversion program to print a heading above the table. Well, that doesn't sound too hard. Can't we just do something like this? Let's give this a shot. Oh, that's not what we expected. At the very least, we need a new line. Well, that looks better. We could put an extra tab in here. That begins to look pretty good. Okay, that completes exercise 1 8.3.